Just так. Okay, so are we ready to start? Of a normal family in the sense of Montel. And that was just, so if y, so x and y are Riemann surfaces, and y is compact, then we said that a family is normal of a family of holomorphic mappings from x to y is normal if its closure is compact. In the natural topology here, that is the compact open topology, if the closure is compact, and this is equivalent to say that any sequence of maps from F has a convergent subsequence. Now what I need to modify in the case when y is not compact. So if y is not compact, I would need to add one case. So let me consider one-point compactification. Одноточная компактификация. Do you all know what this means? So if y is not compact but locally compact, this is always, I mean, if you define Riemann surfaces in the proper way, then local compactness will automatically be satisfied. So y is local compact, and if you have a locally compact space, then there is a natural way of embedded into a compact space by adding just one point at infinity. Let's take a one-point compactification. One-point compactification obtained by adding one point at infinity. I will just write infinity, but this is just a formal symbol. It's just any point you can add. And then you need to define topology here in a suitable way, namely the neighborhoods of infinity are, the open neighborhoods of infinity are precisely the complements of compact subsets of y. So this defines the topology. And convergence to infinity, so a sequence converges to infinity in the sense of this topology if it escapes any compact subset of y. So going to infinity means escaping any compact subset. This is quite natural. And then I say that F, a family of holomorphic maps from x to y, is normal if the closure is compact here in the space of all maps from x to the one-point compactification. I don't claim that this one-point compactification is a Riemann surface. There is no Riemann surface structure, but there is a structure of a topological space. There may be no real Riemann surface structure here, but anyway, this is a topological space, and there is still natural topology there. Is compact, yes. So in more down-to-earth terms, this means that every sequence of maps from F contains either a convergent subsequence or a subsequence that diverges to infinity. Okay? So any sequence Fn has a subsequence Fnk such that either f n sub k converges to something, to f in the whole of xy, or diverges to infinity, diverges from y. No, it's I didn't say whether y is complete or not, but if it's hyperbolic, say it's hyperbolic Riemann surface, then it's always complete with respect to its Poincare metric. So if you consider hyperbolic Riemann surfaces, you always put its own Poincare metric on it, with respect to which it's always complete. So it's not for completion. It's just to say what it means to diverge to infinity. This is the only reason I need this one-point compactification is to make a formal sense of this. Diverges from y means that the images escape any compact subset of y. And this is also called normal. So now, in Milner's book, he proves the following theorem. The definition is a general definition, and it's important that here we do not necessarily assume that the Riemann surfaces are hyperbolic, because a very important special case, which we'll be dealing with most, well, maybe half of, the rest of time, is the case where y is the Riemann sphere, which is not hyperbolic. And it's more interesting than hyperbolic case. Now, to explain why the hyperbolic case is uninteresting, let me quote the theorem. The theorem is that if both x and y are hyperbolic, then what? Then any family then the condition of being normal is just vacuous. Whatever family you take, it will be normal. Is normal. Okay. Now, in Milner's book, you can see a complete proof. But what happens is that Milner actually reproves a standard theorem from real analysis, the so-called Arcella-Ascoli theorem. And you may know this theorem. Do you know it? It's about equicontinuity. Да, теорема Арцелла-Асколи. Ну, давайте я сейчас сформулирую. So what a more general theorem which can be used in proving this fact, and in Milner's book is just proved, honestly. Okay, but a more general thing is, not more general, it's just a general theorem that can be used, but it's not the only ingredient. There will be other ingredients. Another important ingredient is the contraction with respect to the Poincare metric. But another ingredient is the theorem of Arcella-Ascoli, which says when certain family of maps, so suppose that, let's say K is a compact metric space, not necessarily metric, but let it be metric. Let K be a compact metric space, and let B be a metric space. A subset F of maps from K to B. Now this space is just a space of all continuous with uniform metric, because if K is compact, then the compact open topology is just the same as the topology of uniform convergence. So you can take the uniform metric here, and then what we want is the I'm sorry, not an element, but a subset. So you take some family of maps, some set of maps, and you want to know where this family is pre-compact. So a subset is pre-compact in the sense that the closure is compact, if and only if what? Do you know? You don't know. Okay, but please note that there is no complex analysis here. I never say Riemann surfaces or whatever. It's just metric spaces. It's about metric spaces. So it's pre-compact if and only if F is equicontinuous. And I need to define this notion, right? Равностепенно непрерывно это называется по-русски. I'll just say what equicontinuous means. So it's just the normal definition of continuity, but all this definition with different flavors of continuity, they differ only by the order of quantifiers. So F is equicontinuous means that, so equicontinuous, namely, so just a standard definition of continuity is that for every epsilon, so continuous at every point, so for any point in K, and for every epsilon, there exists delta, right, such that if the distance in K between points x and y is less than epsilon, then the distance in B between f of x and f of y, I'm sorry, less than delta here, then the distance in B is less than epsilon, right? This is what it means that a single map is continuous, right? Since K is compact, being continuous is the same as being uniformly continuous. So these two quantifiers can be interchanged. It doesn't matter in which order you put this. So you can write for all epsilon and for all, well, they can be interchanged in any case. You can even put for all epsilon, there exists delta, and for all x put here. This means uniform continuity, right? So that delta will not depend on x, right? So you can put it here, and this is the same thing. But now what does it mean to be equicontinuous? Equicontinuous means that I can write for every epsilon there exists delta for all f from f here. Now if I put this quantifier to the front, that would mean that all maps from our given set are continuous. And we need a stronger statement that delta depends only on epsilon, not on f, not on x. So it does depend on x because of compactness. but it may depend on f, right? And if I require that it do not depend on f, that means equicontinuity. Равностепенная непрерывность. So think of a family of maps, of differentiable maps with uniformly bounded derivatives. If all the derivatives are bounded by the same number, then you get equicontinuity. If the derivatives are unbounded, say at a given point the derivative may grow, then the family is not equicontinuous. Well, actually, it can be still equicontinuous, but this is how this is a way of constructing counterexamples. Okay, so is that clear? Well, I assume you don't know the general theorem, but let me still not prove it. In Milner's book, it's proved inside this one. So it's proved all together, but you can easily separate the two parts. So one part doesn't have anything to do with Riemann surfaces. It's completely general. It's about metric spaces. And this is this criterion. So a family of maps is, well, if you apply it to Riemann surfaces, then normality is the same as equicontinuity. So for Riemann surfaces, local equicontinuity on every compact set. So for Riemann surfaces, I can write that normality is the same as local equicontinuity. Локальная равностепенная непрерывность. Равностепенная непрерывность на компактах. Okay? And now to prove the theorem is very easy. So it's just one sentence. I need to see that I can choose delta independently of f. Now, indeed, I can take delta equal to epsilon and use that any holomorphic map contracts the Poincare lengths, contracts the, well, infinitesimal Poincare distances. Then if epsilon is small enough, that would be enough to take delta equal to epsilon. Do you agree? Голоморфное отображение сжимает длины. Голоморфное отображение сжимает длины. Это теорема Пика, которую... This was Pick's theorem, which we covered. And according to this theorem, all lengths become shorter under holomorphic map. Or maybe the same, if it's a covering, right? Maybe strictly shorter, or maybe the same. In any case, we can take delta equal to epsilon if epsilon is sufficiently small. Right? Just because, so it's, well, it's just saying that all holomorphic maps are uniformly Lipschitz with respect to the Poincare metric, with Lipschitz constant 1. So that equicontinuity follows automatically. It's already, yeah. Может быть, даже для всех, да, может быть, даже для всех. Просто даже если это накрытие, там может быть неравенство, да, ну, то есть это только лучше. Если там может быть еще меньше, чем... Если накрытие, то там не все длины сохраняются, некоторые длины становятся короче, но это нам только лучше, что они становятся короче. Okay. So this means that normality is not a very interesting concept for hyperbolic Riemann surfaces. It's much more interesting for the Riemann sphere. And this is what we will mostly study. But let me also give one corollary. So now another theorem. Suppose we have, so I will not write always that x and y are Riemann surfaces. Well, let me write it like that. This is an abbreviation, Riemann surfaces. X and y are Riemann surfaces, and suppose that y is hyperbolic. Well, actually, maybe I want a special case of this now. Let me just take some subset of y, so then it will also be hyperbolic, open subset. Let me just take an open subset of y. So let me write a picture. So y is something like that. You can think of an open subset of the plane or of the sphere, which misses more than 2 points. Then it will automatically be hyperbolic. And this is the most interesting case for us. And u is some subset of y. So u is inside. Now, you consider a sequence of points in y, say P1, P2, and so on. And you assume that the sequence of points converges to some point on the boundary. So suppose that the sequence of points Pn in U converges to P, which is not in U. So to some point on the boundary. Then for every positive radius, the ball of radius r around Pn converges to P with respect to, so this I should say with respect to which? With respect to the metric in y. In y, meaning with respect to the Poincare metric in y. And here, this is also in y. A ball means the same as the disk because we're in dimension 2. So all these disks of the same radius, they will look like smaller and smaller disks as they approach the boundary. And in the limit, you will see just 1 point. So a sequence of disks convergent to a point means that whatever subsequence you choose here in these disks, all these limits will be equal to P. I meant that the radius is with respect to U. So the ball is with respect to U. But the convergence is in Y. Okay? So from the point, from inside of U, all these disks have the same radius. Okay? But from the viewpoint of Y, they're not disks in Y. They're something, but their diameter goes to 0. And the entire disks converge to 1 point. Is the statement clear? Okay. So how to prove this statement? I assume that Y is hyperbolic. Okay. So the first claim is, the proof is again very simple, but it consists of 2 parts. The first part is that BR of Pn will exit any compactum of U. So for any, let it put it in this way. For any compactum, for any compact subset K in U, BR of Pn is outside for all sufficiently large for large n. For large n. So for any compactum K, there is some number depending on K, such that starting from this number, all these disks are outside. Well, they are outside because otherwise, if they intersect the same compactum, that means that they all lie in the same, maybe very large compact disk in U, which is not the case because Pn escape any compact set. Is that okay? What I use here is that the Poincare metric is complete. Is that if you take a large disk, it will still be compact, compact subset of U. That was the first part, and the second part is that okay, we have we have a family, we have a sequence of maps, Fn, from the first disk, P1, to the disk around the point Pn, just take Poincare isometries. Any two disks of the same radius are isometric to each other with respect to the Poincare metric. Therefore, you can take an isometry. So isometries. And this family of maps can be viewed as a family. So this is a subfamily in here in all holomorphic maps from the disk to Y. Okay? And this is normal. Because Y is hyperbolic, and the disk is also hyperbolic. It follows that any convergent subsequence converges to so what we want to prove is that this sequence of maps converges to a constant, right? To a map to one point. In here. So this is with respect to Poincare metric and Y. It's important to distinguish the Poincare metric and U. So isometries are with respect to U. But with respect to Y, these are not isometries. And in Y, this must converge to a point. How do we prove that this converges to a point? We prove that to prove that something converges to a point, we need to prove that any subsequence contains a further subsequence that converges to a point, right? That would be enough. Do you agree? I want to prove that this sequence converges to P, to the constant map, sending all points to P. for that, it's enough to prove that any subsequence convergence contains a subsequence convergent to P. Okay. If not, да, я считал, что это на анализе первого курса проходит это утверждение. Что если у любой последовательности есть подпоследовательность, которая сходится к данной точке, то и вся последовательность сходится к данной точке. Согласны, да? You know the statement. So again, if any subsequence has a subsequence that converges to a given point, then the sequence converges to the given point. Is that okay? Все согласны? У любой последовательности, у любой подпоследовательности есть подпоследовательность, которая сходится к нулю. Тогда вся последовательность сходится к нулю или к чему-нибудь. Согласны, да? Ну, просто если бы она не сходилась, там можно было бы выбрать подпоследовательность, которая сходится к чему-то другому. А все под... Хорошо. Okay. So, because of normality, in any subsequence has a subsequence that converges to something, that converges to a holomorphic map. Right? To a holomorphic map. Now, what can be the image of this limit holomorphic map? So in the limit, we'll have some holomorphic map, and we now use the open mapping principle, saying that if a holomorphic map is not constant, then its image is open. You know that? So its image is open, meaning that the limit map should map the disk to something like that, to some open neighborhood of P, which includes points in U and also points outside U, right? But that... Да, и что? Ну, саму эту граничную точку он содержит, да? Okay, you made the point, but still, there will be some open neighborhood of P, which contains, well, at least a lot of points here, right? A lot of points of U. Okay, in particular, all these disks will be okay, what I need to say to get a contradiction. Well, all these disks will also be inside, but that is the limit. So they either all coincide or, well, eventually coincide, which is a contradiction because their centers go to infinity. Or, well, anyway, they cannot stay. There will be a compact subset here that will cross all these disks if the limit is like that. If the limit is more than one point, then it will intersect a compact subset of U, and therefore all these disks will also intersect this compact subset, and that contradicts the first part. Okay? So this is a typical use of normality. You want to prove that something converges to a point, and you just look at what this limit map can look like, and you figure out that it cannot be anything else but a constant. Okay. Mm-hmm. Okay. What else should I say about normality? I'm not sure. Maybe just let me go straight to dynamics, because it's already time to go to dynamics. So let me now consider what should I say? Milnor considers a general setting where you have any compact Riemann surface. But let me specialize immediately to the Riemann sphere, simply because there are no other interesting examples. Well, there are some examples related to compact tori, but they are not very interesting. They can be all explicitly understood. So the only interesting things happen in the Riemann sphere. So for this reason, I will stick to dynamics on the Riemann sphere. And I will consider holomorphic maps from the Riemann sphere to itself, from CP1 to CP1. And this is what? You probably know from complex analysis that any holomorphic map from the sphere to itself is just a rational function. So algebraically, these are very easy to describe. These are rational functions. Of the form f of z equals to some p of z divided by q of z, where p and q are polynomials. P and q are polynomials in z, maybe of some degrees. Now, an important notion is the degree of the rational function, and the degree of f is what? How do you define the degree of a rational function? No, not minus. It's the maximum of the degree of p and the degree of q, and this has a good reason. You want this algebraic notion of degree to coincide with the topological notion. So topologically, if you have a map from the sphere to itself, then there is a well-defined degree. How do you define degree? For example, the map induces some homomorphism on, so this is a two-dimensional sphere, and the map F induces some homomorphism on the level of P2. So P2 of CP1 is mapped to P2 of CP1. You know what P2 means. It's the second homotopy group. Do you all know what this is?
I don't know all details about P2, but I know some.
Okay, maybe it's not necessary. Let me say it simpler. So this is an algebraic definition of the degree, and believe me, the algebraic definition is this, not the minus. Even for algebraists, it's not the minus, it's the maximum. The meaning of this definition is what can be explained in a very simple way. So let me state it as a theorem. So maybe before stating the theorem, let me say that critical points of f are the points where the derivative is 0. The point z where the derivative is 0, which may be not the best way of defining this, but, well, algebraically it's easy to compute, except when z is equal to infinity. But if z is equal to infinity, you simply rotate the sphere and send z somewhere else, and then compute derivative. So you make a conjugacy. Well, not even conjugacy. You simply change coordinates and send z to some other point, and then compute derivative. So critical points are where the derivative vanishes, and if a rational map is non-constant, then this is a finite set. So this is finite unless f is constant. So the critical values are defined as the images of critical points. Okay. Let me also use some abbreviation. Say CV of f will be critical values of f. And theorem. If you restrict f to the sphere minus the set of critical points, no, not the set of critical points, you rather take the full preimage of the set of critical values. Okay? And this will cover the complement of the set of critical values. This will be covering in the sense of topology. Okay, so it evenly covers the base of degree. And now I refer to the notion of the degree of a covering, which you should know, right? Of degree equal to the degree of f. So the degree of the covering is the number of points in every fiber, right? All fibers, since this is a covering, all fibers consist of the same point. And if you count the points in any fiber, you should get the same number. And this number is exactly this. So all this theorem is just the what? It's the inverse function theorem, right? It's another the inverse function theorem. Ну, там нужно, чтобы это было конечно-листное, но, в общем, там нужно что-то потребовать, если вы хотите другие Римановы поверхности. Поэтому я формулирую это для рациональных функций. Нужно, чтобы конечное было, конечно-листное накрытие. Ну, иначе там, кроме критических точек, будет, в общем, еще некоторые другие. Нет, ну, это вот именно для, как я сформулировал, это именно для рациональных функций. But this reduces to the inverse function theorem, because if you take any point from here, then any point of the fiber is a non-critical point. Therefore, you have an inverse branch, right? By the inverse function theorem. And you have a collection of inverse branches which gives you a trivialization of this covering. And you will have exactly d of those. Why? Because you can write an algebraic equation, and you will see that this algebraic equation will have exactly this degree, right? You fix a point in the base, so you fix u and solve what? P of z divided by q of z is equal to u. U is fixed, so this is a constant. You multiply by the denominator. You have a polynomial equation of that degree, right? Okay. So now, a very important concept in complex dynamics is that of the Fatou set and of the Julia set. Let me give a definition. I know what I forgot. I forgot to state Montel's theorem, which is really very important, but it's an easy consequence of what we discussed. So let me first give a definition of the Fatou and Julia set, and then I state this theorem. So the definition is as follows. The Fatou set of F sometimes people write F capital of F. Is the union of all open subset of all open subsets U in the Riemann sphere such that the family of iterates, so this is the nth iterate, you iterate fn times, and in this way you get a sequence of maps such that the family of iterates viewed as a map from U to CP1 is normal. So in other words, this is the largest open set on which the family of iterates is normal. Normality is a local notion. So if it's normal on all open subsets, it's also normal on their union. Therefore, the Fatou set is the largest open set on which the family of iterates is normal. Okay? And by definition, it's always open. It's just one, well, it's just explicitly stated in the definition. And the Julia set is by definition G of f, is by definition the complement of the Fatou set. CP1 minus the Fatou set. The choice of the names, Fatou and Julia, for the two sets was somewhat arbitrary because people wanted to give credit to both Fatou and Julia. These were French mathematicians who worked in the first half of the last century. And they made initial contributions to complex dynamics. After their contributions, the field essentially died for about half of the century. And it was revitalized in 70s, 80s. But this classical period, so both Fatou and Julia gave this definition, and this was a random choice. So basically, one set is equivalent to the other because they're complementary to each other. And one is arbitrarily named for Fatou and the other for Julia. Now, by definition, the Julia set is compact. So J of f is compact, again, by definition, because it's a complement to an open set. Therefore, it's closed, and any closed subset of a compact space is compact. Да? Что? F у нас рациональная функция. F вот здесь. Я рассматриваю глобальные рациональные функции сейчас. Угу. That if you have two sets, open sets, and on each of these two open sets the family is normal, then it's also normal on their union. Yes, it's true. Because normality is a local notion. Yes, on every compact subset of the union, you take well, you take a compact subset of the union, represent it as the union of well, I guess you can represent it as a union of two compact sets, one of which lies in one open set and other lies in the other open set. Now you can choose a convergent subsequence on one compact set, choose a further subsequence on the other compact set, and that would be convergent subsequence. Mm-hmm. Okay. Now let me state the theorem that we will need in order to study Fatou and Julia sets, and then I will talk about some examples. Да. А дело в том, что нормальность, она формулируется в терминах, мы сначала выбираем компакт, а компакт всегда покрывается конечным числом открытых множеств. Даже если у вас бесконечное объединение, в нем надо взять компакт и там смотреть, что происходит на этом компакте. А компакт всегда покрывается конечным числом. So even if you have an infinite union of open subsets, normality, the notion of normality is formulated in terms of compact subset, and every compact subset lies in the finite union of open sets. Так, хорошо. Вот мне нужна будет такая теорема. Montel's theorem. Well, this basically reduces to what we discussed, but let me still state it. F, so let U be open subset. Then any F, any family of holomorphic maps from U to, let me put it in this way. If a family of holomorphic maps from U to the Riemann sphere misses 3 values, means that is such that for all maps from this family, f of u is disjoint from A, B, C. A, B, and C are different points. So there is a 3-point set from which all these images are disjoint. Then F is normal. Well, the key point here is that if you remove 3 points from the sphere, you get a hyperbolic Riemann surface. Now, you need still to say something. If you consider F as a family of maps to a hyperbolic Riemann surface, it will be automatically normal by the theorem we proved. But I claim that it will also be normal as a family of maps to the Riemann sphere. Because why? Because convergence in the Poincare metric, when you remove 3 points, is even stronger than the convergence on the sphere. So if some sequences converge in the complement of 3 points, then they also converge on the sphere, right? And that's it. So this is basically a formal consequence of what we discussed. And this will be a key technical tool. Actually, Montel developed this theorem, proved this theorem exactly for the needs of complex dynamics. Okay. Now what should? Well, by definition of normality, it has to do with the compact open topology. So what it means to have a convergent subsequence? That means that on every compact subset, you can choose a subsequence that converges uniformly on this compact subset. Ну, главное, чтобы можно было все исчерпать счетным числом компактов, а тогда мы как-нибудь подпоследовательность выделим. Это называется, как называется, диагональный трюк. Если можно для каждого из счетного числа компактов выделить последовательность, то можно и одну подпоследовательность выбрать. Берете первый член первой подпоследовательности, второй член второй подпоследовательности, третий член третьей подпоследовательности и так далее. потому что она будет под последовательностью в каждой из вашего счетного числа подпоследовательностей. Поэтому если каждая из них сходится, то это подпоследовательность будет сходиться. Нет, а мы каждый раз подпоследовательность будем выбирать. Мы на первом компакте выберем подпоследовательность, на втором подпоследовательность этой подпоследовательности и так далее. Ничего страшного. Возьмем первый член первый, второй член второй и так далее. Хорошо? I don't think these details are very important, actually. They are, I mean, okay. So let me now give an example where you can figure out explicitly what the Fatou set and the Julia set are. So an explicit example, unfortunately there are very few such explicit examples, but one of them is f of z equals to, well, let me take z to the n, where n is bigger than 1. So just a polynomial, which is the nth power of z. And I claim that the Fatou set of this polynomial is everything but the unit circle. So CP1 minus the unit circle, the set of all points with modulus equal to 1. So if the modulus is not 1, then the family is normal. Okay? So indeed, if you take the interior, then all iterates inside the unit disk, all iterates converge to 0 uniformly on every compact set. Therefore, they converge to 0 in the compact open topology. Okay? Outside the unit disk, all iterates diverge to infinity, also uniformly on every compact set. Therefore, in the compact open topology, and that makes all those families normal because they converge, right? So their closure is compact. I proved that the Fatou set contains everything but the unit circle. Now, it cannot contain the unit circle because if you take any point of the unit circle and any neighborhood of this point, it contains points that diverge to infinity and some other points that converge to 0. Now, the limit map would have to take only two values, 0 and infinity. And there is no holomorphic map like that, taking two values, right? So it will not have a limit. Alternatively, you can compute derivative on the unit circle and figure out that this derivative, that the modulus of this derivative is what? Is n to, well, anyway, it grows with the iterate exponentially fast. And therefore, again, there is no convergence. Because if you have convergence, that the derivatives should also converge. And now the derivatives grow. They cannot converge. So intuitively, you can think of the Fatou set as the set where you have stable dynamics, and the Julia set as the set of where you have unstable and, well, informally speaking, chaotic dynamics. And you always have the splitting of the sphere into these two sets. Okay. So let me state some of the basic properties of the Fatou and Julia sets. So probably maybe the most important property is that they are fully invariant, meaning that the full preimage of the Fatou set is the same as the Fatou set. It's stronger than saying that the image of the Fatou set is the same as the Fatou set, right? It will follow. If you take the image, then it will follow that the image is the same as the Fatou set. But if you take full pre-image, it's stronger. If you just say that the image of a set lies in this set, then the set is called forward invariant. And this means backward invariant or fully invariant. Full invariance implies forward invariance, but if you have a forward invariant set, then the full preimage may be larger. Так, хорошо. Why this is so? I want to say that if let's take this, and let me call this set U. I want to show that U lies in the Fatou set, right? And what I use is just the definition. By definition, I need to take the family of iterates and prove that this family of iterates is normal on U, right? But the family of iterates is just a subfamily, so the iterates on U. So I want to, that is, i.e., the family of iterates is normal on U, which is equivalent to saying that f to the n minus 1 is normal on f of U. Do you agree? And we know that, because f of U is in the Fatou set. So we just set one iterate, and we don't spoil the normality. We keep the normality. Therefore, the full preimage of the Fatou set is the Fatou set. Therefore, the full preimage of the Julia set is also the Julia set. Do you see why this follows? Yes. Since f is forward invariant, the Julia set, the full preimage of the Julia set lies in the Julia set. But it cannot be strictly smaller because well, again, because of that. If it gets to the Fatou set, the preimage must be also in the Fatou set. So in general, f минус 1. Здесь? Здесь? n минус 1. n минус 1, но на f от u, да? Понятно, нет? То есть вы одно f сделали, и дальше вы делаете остальные n-1 итерацию. Если вот такая последовательность будет сходиться, то будет и f в степени n сходиться на u. Okay. Well, this is a general fact that if you have a fully invariant subset, then the complement of this fully invariant subset is also fully invariant. You can prove it easily. This is a set theoretic claim. Now, the Fatou set may be empty. This happens. But the Julia set can never be empty. Theorem. The Julia set is always non-empty. Proof. Other ways. So what would be, so assume the contrary. What would be the contrary statement? The contrary statement would be that the family of iterates is normal on all of the sphere, right? That means that there is some convergent subsequence, right? So then there is some subsequence of iterates convergent to a limit, to some g. And g will be a holomorphic map from the Riemann sphere to itself. That is a rational function. A rational function of some degree. Okay? And the convergence is uniform because it's uniform on compact sets and the sphere is compact. Okay, G has some degree, and if you have a convergent sequence of maps, then the degree stabilizes. It must, for all nk large enough, the degree of this must be equal to the degree of G. Do you know why? Because if two maps from the sphere to itself are close enough, they are homotopic, right? It's enough, close enough, it's too much. What you actually need is that the images of the same point under the two maps are not as far as the opposite points of the sphere, right? If you have that, then you can always connect the two images by the shortest geodesic, and then you have a homotopy that connects one map to the other, and homotopic maps have the same degree, right? So since this sequence of maps converges, then eventually they will have the same degree, right? So for large nk, the degree of the iterate will be equal to the degree of G. But on the other hand, the degree of this is what? Is the degree of f to this power, right? It's just because you know how to count preimages. In order to count preimages under the high iterate, you need to count the preimages under the first iterate. Then take the preimages of the preimages. There will be d to d squared. Second preimages, there will be d cubed third preimages, and so on. Okay? And that's a contradiction, because the degrees grow, and on the other hand, they must be the same. So it's because this effect. Now, the Fatou set may be empty. Let me give an example. Mm-hmm. Ну, там было, в общем, эквивалентное определение, потому что если то определение, которое было на первой лекции, оно сводится к равностепенной непрерывности. Стабильность — это то же самое, что равностепенная непрерывность этих самых итераций. So this must be the same, but there are alternative proofs. Actually, Milner also gives alternative proof. You can look up there. So there is an example where the Fatou set is empty. So let me describe this example. So let's consider the linear map. Z goes to 2z. So this linear map is from C to itself. Is that okay? Now, let me take the quotient So I want to project C to the torus, say Z plus IZ. So I just choose some lattice. It doesn't matter, just any lattice. Lambda here, lattice. Lattice means a subgroup generated by two linearly independent vectors, right? C mod lambda. So this is a Riemann surface, a parabolic Riemann surface, a Euclidean Riemann surface, right? But the map can be descended to the level of this tori because the lattice is stable under this map. Okay, so there is some holomorphic map G over here from the torus to itself. Now let me take a further quotient, and the further quotient would be identifying Z with minus Z. What would be this quotient? So I claim that this quotient will be just the Riemann sphere. There is, we need to define a complex structure. So the complex structure is obvious except for points where Z is the same as minus Z, except for 4 points of the torus where Z happens to coincide with minus Z, because outside of these 4 points, this is a covering map, and the complex structure descends. Now, if you have a complex structure everywhere but at 4 points, then by the removal singularity theorem, you already defined the complex structure everywhere. So this... Откуда мы знаем, но мы можем явно... Ну, в 2 слоя там склеится. Проколотый диск накроет что-то, но если там было... So if you had a puncture there, therefore you can draw a small circle around the puncture. Then after double covering, you will also have a puncture. You will also... Прокол. Это, ну, значит, мы что-то выкинули. Вы говорите, а почему мы выкинули только одну точку? Это очень просто понять на уровне Римановых поверхностей. Обведите то, что вы выкинули кривой. Если эту кривую можно сделать маленькой, то это одна выкинутая точка. Если ее нельзя сделать маленькой, в смысле метрики Пуанкаре, то больше. Вот и все. Потому что это накрытие. Накрытие — это локальная изометрия. У нас одна проколотая окрестность накрывает другую проколотую окрестность. Well, anyway, maybe I should explain why this is topologically a sphere. Do you understand why this is topologically a sphere? It's not hard. So let's take the fundamental region for the lattice. Let's assume that the lattice is just the usual one, the integer lattice. Okay? So this is the fundamental square of this lattice. And let me put this fundamental square like that. So this will be 0. Okay? This will be 1/2. This will be minus 1/2, and so on. And you have the usual identifications on the boundary, right? So this side is identified with this side, and the top side identifies with the bottom side, like that. Now, you also want to identify by the map Z goes to minus Z. So this is another equivalence relation. Now, let's note that if you take the right part of the square, then so say take the closure of the right part, the closed rectangle like that, then all orbits, either z or minus z, will get there, right? So so the quotient by this equivalence relation can be glued from this rectangle, right? The only thing we need to do is to identify some points on the boundary, namely, there is a point z here on the boundary which should be glued with the point minus z here. That means that this side should be glued with this side, and similarly this side should be glued with this side. And this is called the pillow. You take a sheet of paper, and how you glue? You glue like that. You fold it and glue it on the boundary. Now, if you put some stuff, if you stuff it from inside, then what you see is a pillow, right? And the pillow is topologically a sphere, except that it has 4 corners, right? These 4 corners geometrically look different, but from the point of view of complex structure, these are the same as just regular points. So what you get here is CP1, and you can also, and this map also descends to CP1 as a rational function because it will be a holomorphic map, right? Moreover, you can write an explicit formula for this rational function. This is called the Weierstrass P function. And you can write it down explicitly. You can write down explicit series. Not this. This is the Weierstrass P function, and this is a rational function, which gives the argument Dublin formula for the Weierstrass function. Anyway, if you look at elliptic functions textbook, что вот эта функция Weierstrassa, которая склеивает, а вот эта рациональная функция, которая, это называется формула удвоения аргумента для функции Weierstrassa. А именно p от 2z можно выразить как рациональную функцию от p от z. Вот это называется формула удвоения аргумента. Вот, и здесь вы видите вот эту рациональную функцию. Ее можно написать совершенно явно, явной формулой. So you can write down an explicit formula for this rational function, and that gives you the formula for the argument Dublin of the Weierstrass function. And I claim that this rational map has empty Fatou set because the derivative, so if you look at the derivative here, it grows, therefore the derivative here also grows. So this is an informal argument, but you can add details and prove that this is. Да. Да, z переходит в 2z. n-ная итерация, это z переходит в 2 в степени nz. Да, то есть производная, она постоянная и везде одна и та же. А из этого следует, что эта производная тоже будет расти. Ну, за исключением, тут будут критические точки. Конечно, те точки, которые попали в критические, там производная, раз уж стала нулем, там она так и останется нулем. Но за исключением этих точек производная будет расти. Поэтому, so if you don't get to the critical point so far, then the derivative will grow. Так, ну. Есть вопросы? Any questions? Ну тогда все. Функция Weierstrassa от 2z – это r от функции Weierstrassa от z. То есть, если вы знаете функцию Weierstrassa от z, то вы можете посчитать функцию Weierstrassa от 2z, ну, применив некоторую рациональную функцию. if you'd like, we can do this exercise and write down an explicit formula for R next time. But tell me now so that I can get prepared.
Выбор либо это, либо что-то в конце побольше динамики, или просто чем больше вы скажете?
Нет, ну я что успею, то успею. Я не могу... Про то, что будет в конце, я не могу обещать, потому что это я должен знать скорость, с которой как бы я... Угу. Угу. Ну, можно найти, да. Ну, хорошо. Нет, ну, в принципе, все что... Да, нет, все, что я рассказываю, можно найти. Более того, в основном это можно найти в книжке Милнера. Вот этого конкретно в книжке Милнера нет, так что, я готовлю вот это, нет?
Давайте в конце, если останется время.
Ну, хорошо, ладно. Тогда в следующий раз не про это, а в конце, если останется время, про это.